We are starting up slowly. We have some people joining, so I'll be spending one more minute to let everyone in. So it's getting a little late here in Ukraine, so we have some guys probably joining it a little bit later here and there. So, well, one question proposition to all of you. If you are not intended to speak, please mute yourself when you log in, so we have better sound quality for everyone. So let's wait half a minute more and then we are good to go, I think. So I think we are starting up now. So good evening to everyone. My name is Alexander Lubimov. I am Business Director of EKTOS Development, and I will be today your host, making this presentation about TinyML use with STMicroelectronics tools and their tool chain called Nano Edge AI Studio. So let's move on. So let's talk about EKTOS for a very few seconds, just to remind you about who we are. So we are Danish-born consultancy, started by two engineers back in 2007, Viborg, small town in Denmark. Now we are 120 people across 3 business areas, namely electronics development, that's what I'm representing this evening. Then we have type testing and approvals department and electronic manufacturing services, where we deliver electronics to our clients. So we have 6 offices across Europe, some in Denmark, some in Ukraine and in Slovenia. And in my department, we have 53 engineers now doing different kind of developments for hardware, software, and obviously machine learning as well. And we have more than 50 IoT projects where we have been using machine learning in particular. For today's presentation, which we are doing together with ST, we have me here at the left side. Then we have Mr. Pierrick Autret, who is Product Marketing Manager of AI Solutions from ST. Then we have my colleague, Darina Nedilko, who is our Machine Learning Engineer and Data Scientist at EKTOS Development. So this webinar is combined effort between EKTOS and STMicroelectronics. EKTOS is the only STMicroelectronics partner in Ukraine and one of the few ones in Denmark. We have been one of the first ones working with a very well-known graphical interface toolchain called TouchFX. So actually we have pretty long and good legacy working with ST, and we have been doing like I don't know, 4 or 5 dozens of products based on ST processors. So today we'll be talking actually on Nano Edge AI. You can see I'm pointing on the screen the green one. That's Nano Edge Studio, as it's called at ST. And actually ST offers a little bit more sophisticated, for more sophisticated models, they offer yet another tool that is called XQBI. That is more tailored to, I would say, sounds and video processing that we will not touch this evening. The important point, which I also want to stress for everyone, is that NanoEdge AI became totally free very recently from 6th of December. And you can basically read about it here in the news. So that's really important. They had some limitations before, but now it's fully free. So what we'll be talking about today is actually NanoEdge introduction by Pierrick, our colleague, and he will not be presenting during this presentation by himself. So actually, ST recorded a video for us, so he will be playing it. Then we'll talk about the practical case, which we have been presenting to you before. Then when we went through the case, I will actually pass the microphone to the Rina, who will be actually going through the tool and the way it can be used in a detail. And then we'll end up wrapping up our experience and also do some recommendations and advices to you how to use the tool, how to be effective with the tool implementation in your products. All right. So let's move on to the ST part, and this part will be with the video right now.
Hello everyone, I'm Pierrick Autret and I'm Product Marketing Manager at STMicroelectronics. Today, we will discuss about Nano Edge AI Studio and how to make Edge AI a reality. Speaking about reality, this is a real product deployed on the field, as you can tell with the picture. This is a pump, and this is my boss pump. So my boss is really happy and proud about this pump. It was one of the best in class when he bought it. It makes its jobs perfectly, pumping water. My boss is living in New York, and a few months ago, a huge storm hit them. The thing is, at this exact moment, this pump was not 100% efficient due to some debris which have been collected during previous storm. The pump was partially clogged, and it resulted into a flooding in my boss' basement. So what can we learn from that? A great product is not enough anymore. Today, products can and should adapt to their environments to provide some meaningful information and to be able to react to unplanned events or conditions. The definition of a great product is changing, and the customer expectations are changing as well. Products need to be a bit smarter. You will tell me, Pierrick, there is a lot of smart products already, smart TV, smart lighting, smart vacuum cleaner, for example. Okay, right. The thing is, these products are not actually smart. They are connected. And the fact they are connected help us to manage them through a dashboard. And thanks to the information that the data that these products are sending, you are the one who is making the smart decision. Some of the products can make decision by themselves thanks to, let's say, advanced algorithm or machine learning or AI. Most of these algorithms are running on this kind of platform. So on huge server, on greedy application processor, and so on. The thing I want to highlight today is the fact that we can make this intelligence, this AI running here on, let's say, a really tiny and cost and energy effective microcontroller. This is actually what we call Edge AI running on devices on the edge. There is a lot of benefit of using Edge AI, and to list some of them, it's allow to create some real-time application because you're reducing the data transmission, so you don't need to wait for the inference result to come back to the endpoint. By definition, because you're not sending raw data all over the time, you are limiting the risk and the backdoor, so you can create more secure solution, and also you can create more energy effective solution because we know that sending once again raw data all the time is really power consuming. In order to create some AI based solution, you need to go through a workflow, which is, let's say, a basic workflow in AI creation, from data collection, clean the data and pre-process the data, then to select a machine learning model or deep learning model, to train this model, and then to deploy it on the field. This workflow is not, can be tricky for some people who don't use to play with machine learning model. The thing is, at ST, our goal is to make the creation of Edge AI solution simple, rapid, and more cost-effective than any other technology. In order to reach this goal, we need to adapt our ecosystem to propose some tools to allow any developer to have access to this technology, which is AI. Because we know that a big part of embedded developers don't have AI skills yet, we are proposing for more than 4 years now Nano Edge AI Studio. So Nano Edge AI Studio is the perfect tool to create and to generate machine learning model from scratch. So you don't need to have any AI skills. Any embedded developer, any single embedded developer can create a machine learning with a model with this tool. This tool is proposing the state-of-the-art of machine learning algorithm. Thanks to a regular release, we have more than 10 patents today on this tool, and you can generate some optimized machine learning model for any Cortex-M based microcontroller on the market. Thanks to this tool, you can create some various models. So anomaly detection model, if you want to detect any abnormal behavior on an equipment, for example, or if you want to create some classification algorithm to identify the activity, the environment, the usage of an equipment, but also to create some extrapolation, some regression models. Regression model makes some correlation between noun and unknown values to predict future states. For example, to predict the value of a sensor. How Nano Edge AI Studio is working. A huge benefit of the studio is the capability to benchmark in matter of minutes thousands and thousands of combinations of machine learning model, hyperparameter, and preprocessing blocks, enabling smart feature extraction, for example, and many more. The best combination for your application will be compiled into an optimized library ready to run on any Cortex-M based MCU, from the M0 to the high performance MCUs. Thanks to this, it's feasible thanks to the size of the machine learning model themselves. So the library are between few kilobytes of flash and RAM in order to be able to run in any situation without external memory or without a dedicated MCU. Actually, this tool is more complete than you think. In the studio, you have plenty of different tools in order to help you and to support you from the beginning to the end of the project creation. For example, the sampling finder will allow you to find the best sampling size and sampling rate for your data collection. Talking about data collection, we have a data logger generator. So you just have to select the board, the sensor, the frequency, which have been found thanks to the sampling finder, and you can generate a data logger file that you can just drag and drop into your board and start your data collection. Then, when you have your data, you can use the data manipulation tool to clean and to reorganize your data in order to have the best performance once you will benchmark the models. To come back to the AI development workflow, I want just to highlight that Nano Edge AI allow you to help you through all along this workflow, from the data creation, the dataset creation, to the model implementation and to an MCU. So it helps, once again, any embedded developer to create some AI optimized model, even if they don't have AI skills, but also it can help some skilled engineer or developers. One more thing which is really important. Let's take an example of a real application, such as predictive maintenance, for example. So we know that even if on the datasheet two equipment are the same, they will act, they will behave slightly differently because the environment, because the usage. So, for example, the vibration pattern or the noise or every kind of signal will be slightly different from a pump to the other. This is why creating a generic and static model in order to monitor the health of this equipment, this pump, is a nightmare. It's really challenging because you have to take in account any kind of behavior, from any pump, and to be sensitive enough to be able to detect any drift. Thanks to Nano Edge AI Studio, you can generate some anomaly detection algorithm with on-device learning capabilities. This means that the model can learn the pump behavior directly on the microcontroller. You can train your model directly on the MCU, which is mind-blowing. You don't need any computer to retrain your model, and you can just switch from inference to train in order to fine-tune and adapt your library for each single pump. So thanks to that, you have a fine-tuned library which is optimized and really accurate to limit the number of false positive and false negative. And every single pump have its own tailored machine learning model to be able to monitor its states. So you can apply that to pump, as I was mentioning, for example, to detect clogging, but also to motors, to detect bearing issues and so on, but also to circuit breaker, for example, where the arc fault detection is a real challenge because it's the first reason of domestic fire. But there is a lot of other applications. So let's take another example, this time in home appliance, and more precisely in white goods. So we create this proof of concept in order to show how AI can help to optimize the washing cycle in a washing machine. Actually, we are quite convinced that thanks to an accurate weight estimation, we can reduce the water used and the power consumption as well. The thing is, we didn't want to add any sensors or any MCU microcontroller to create this new feature. So we did implement the machine learning model from Nano Edge AI Studio on the microcontroller which is managing the motor control. By taking into input the signal, the current value, we can approximate the weight in the drum. So for example, here my colleague is putting 400 grams, and the model have been trained with some value of current associated to some value of some weight, and the model will create some correlation, the rest of the correlation between all other signal weights combination. So here my colleague put 400 grams plus 800 grams. If I'm not wrong, it's 1,200 grams. And the output of the machine of the model is 1,244 grams. So less than 50 grams of uncertainty, which is better of the state of the art actually. The model is really accurate. So with several tests, we are under the limits of 100 gram accuracy. And today, state of the art in washing machine vendors is something like 200 or 250 gram of uncertainty, which means that our team, which are not at all machine learning experts, did in a matter of hours, thanks to the Nano Edge AI Studio, a better solution than most of machine vendors. This is applicable to smart white goods, but a lot of other applications, for example, smart lighting, thanks to people detection, to detect people in the room and to turn the light off when nobody is in the room anymore, or to optimize the heating system, and so on. Actually, there is a lot of application. It's difficult to be exhaustive, but you can have a look at stm32ai.st.com to have more. information about what kind of use case we can address. Thanks you.
So that was the presentation by Pierrick, marketing product manager of AI solutions at ST, and that was really, exciting to heat up our further discussion, our further presentation. So now you know how ST positioned their tool, and actually we like very much the way the tool chain is done. So to be able to pick up from here and actually build our discussion on a more practical case, let's recap the previous presentations. If you have been attending, you probably remember it. If not, you will see what we have been solving. So the task we have solved with my team that we really want to present today was actually the detection of proper cleaning at the premises. So the idea is very simple. We have some data that we can analyze in terms of cleaning duration, particular relative humidity rise, and then change in volatile organic particles and CO2. And by analyzing that, we can inform one single bit of data saying if the cleaning of premises was good enough or not. So that was the solution we have done. Actually, for the customer product, the task was solved initially using ESP32 and their Espressif toolchain. But later on, we have decided to migrate it to ST, and that's what actually generated some really eye-opening experience for us as well. So that's our case. So we have the board, we have some sensors available for us, and we want to end up with one single bit of data or one single bit of solution saying if the cleaning was done in a proper manner or not. So if you look into actually development life cycle of machine learning projects, then basically just to kind of recap super fast, we have classical things like requirement clarification, architectural diagram that we want to build. We have data logging, and then after data logging is done, so we actually have the data to work with, we go to actual data mining and data processing, where we have a data scientist and product owner working together, trying to figure out how they can actually extract some events, what actually happens from the data, and then they can label the data. Then when the labeling is done, then we go to actually model development and training and validation, and then with the help of software people and quality people, we actually do porting into the actual hardware, testing stuff, and kind of circulating back if you don't like the data we obtained from the model. So that's the whole process. If you're doing it, it might actually circulate several iterations before we have the machine learning data model that is good enough for solving the problem, like what Pierrick shown on his video. I'm pretty sure that they have been dwelling several cycles here and there in order to have the weight assessment to be so accurate. So what the ST Nano Edge AI covers? Well, it covers actually pretty big chunk of work here, meaning we can start with data logging, we can do all the manipulations with the data, generate a model, train it, validate it, and then actually get our library ready for porting being constructed here. So that's what it can do, and that's what will be kind of crunching this evening. So that's my part of the presentation. Now I want to switch control to Darina. So Darina, stage is yours. Please explain us how to use this brilliant tool.
Hi all, thank you, Alexander. And let's start with the interface. Let's get to know our Nano Edge AI Studio tool. So when we are starting the project, we should find some inspiration, right? So the first step for us would be go to this right bottom corner, and to find some projects we want to mimic or we want to look up to. And then the next step for us would be, of course, get to know how the libraries work to find some guides how to do some sort of things. The third step would be find some data, prepare this data, and move on to the step number 4, to the starting of a project. And based on the link, on the information we've got in documentation, we can choose our type of our project. And after we finished, we can move to the step number 5. We can see our projects ready here. And in case of some new data coming or some changes, we can easily have them back and rerun our benchmarks to obtain new version of a model. Of course, everything is accessible in this fast access menu. Here, our last 3 projects and data manipulation tools. So let's talk about data we used for our case. As you probably know, if you attended our last webinar, we collected our data by ourselves. We didn't use the EST tool data logger to develop some firmware for that. We used ESP32 device to collect it. So we collected a lot of data with 5 sensors in it. This you can see on the screen. And we made a special person to record time steps where cleaning was started and ended. And we got this little pretty file. Then we made some exploratory data analysis and found out that the best window size for us would be 128 records with the stride of 10 seconds. After sampling and labeling of our data, we got this beautiful image with labels in it, and this green thing is sliding window. In further presentation, I will talk about window as a buffer, because it is how the NanoEdge's app says. They denote it as a buffer set of records. And then to make everything clear for us, we need to define prediction flow. So for us, it would be that first model is ported, we turning on our device and waiting until the full buffer is filled with valid information. And only after filling the buffer, we can get our first valid prediction. And other predictions will be coming after 10 seconds of waiting. So to get our first prediction, we should wait at least 21 minutes, and then we will have this full sequence of predictions that are valid and can be used to portray it on our UI. So how can we do this with NanoEdge? First off, we should build our data logger. This is a tool that helps us to build a firmware in order to collect data from sensors. First, we need to choose a target. Then we need to choose the sensors we want to record, give them some settings based on our own consideration or other tools. And of course, we need to remember that there are 2 types of sensors: continuous sensors and basic sensors. I will tell the difference a bit later, but we need to remember that continuous sensors are the ones that stream data at their maximum rate all the time without stops. So the next tool would be for us is data manipulation. Here we can perform basic data preparation like feature extractions, extract the axis we want to predict on, and we can delete some outliers. For example, if we are waiting until the buffer will fill, we can delete the first 127 records because they are redundant for us. They're wrong, right? We don't need to predict on them. And then here we can shuffle data and reshape it however we want. And the third tool would be sampling finder. We can as well use it before logging or before data preparation, but I would recommend first collect some data, then use sampling finder to find the best sample size, to find the best buffer size. And only after that, we can proceed with further predictions and developing of a model, because data quality here is important. Unfortunately, we cannot deal with libraries by ourselves. Everything is done for us. The only thing we can do is just prepare our data in a good manner, in a good way. And then model selection. So there are three main types of tasks that NanoEdge can do. It is extrapolation classification tasks and anomaly detection. Two tasks of classifications are one-class classification and n-class classification. N-class is when we're talking about, for example, we need to find dogs, cats, or mouses. And when we talk about one-class classification, is we need to define, is it a mouse or not? For example, is it a normal behavior or not? When we're talking about extrapolation, by extrapolation, we usually mean regression models. These are models that can predict something in terms of time. So, for example, we know we have sales for past decade, and we want to predict sales for the next 2 years. Extrapolation task is the task we need to tackle. And anomaly detection. Anomaly detection is usually used to detect some outliers, some anomalies in our data, that is something is not working properly and is skewed. So to address our issue to detect cleaning, we have decided to experiment with two types of models. Well, actually 3, but I will come to it later. The first one is anomaly detection. Anomaly detection is when we have abnormal behavior and normal behavior of our target of our data. And we need to predict, we need to find which exactly in continuous data, which behavior is good and which is bad. So first we upload some bad and good samples to the model, and after we deploy that, we can get some predictions on our current data. And the second project is one-class classification. It is slightly similar to n-class classification. I will cover it a bit later. And you need to know that one-class classification is the task that requires only normal data samples. Other types of samples that are not like normal would be considered abnormal. You need to remember that. So in our case, we defined cleaning state as normal state and uploaded only one data set with cleaning. In anomaly detection, we uploaded 2 data sets with clean and non-cleaning samples. Model generation step. So here is the UI of our app. We usually start with initializing the project. Then we go to uploading our signals, uploading our data. Step number 3 for us will be running a benchmark. By benchmark, we mean finding the best library for the case, the one that would give us the best results, best performance. Steps number 4 or 5 are mostly for validation of our library, for checking on specific cases, specific data sets. I will cover it later. And number 6, we compile our library. We compile a project that will eventually be deployed on a target. And of course, don't forget to use your tips, your virtual guide, if you have no clue what to do, it will definitely guide you and will give you some tips what to press and what to do in order to get at least some result. And first step is initializing the project. The most important here is RAM settings, flash settings, and of course you need to choose your board and you need to choose your target to optimize your library up to this target. Don't forget to add some meaningful description because it may be handy in the future. Don't be lazy. And here we see that we need to define number of axes. By axes, they mean here number of sensors. So when we are talking about a project that has 5 sensors in it, we will leave 5 here. And sensor type. In our case, we use generic sensor type because we have multiple sensors. But if you're working with some certain types of sensors that have more than one or just one or more than one axis, you can choose one of these types here. I know that guys who will build a firmware using NanoEdge will definitely know what to choose here because the terms, the vocabulary here and there are similar. Talking about data, we should definitely mention some differences between anomaly detection and one-class classification. First, of one-class classification gets only one data set with good examples, with normal behavior cleaning signals. And anomaly detection will require 2 data sets with normal and abnormal data. Even though you don't have many data, you don't need to worry because anomaly detection is a special type of project, and I will cover it a bit later. So the rest is pretty similar. You have to load your data. You have to have your data in buffers in Windows. Your buffer size has to be a power of 2, and minimum lines in each axis should be 20. We personally uploaded 27K lines for each class, and buffer size for us were 128, which is a 7th power of 2. 2 in 7th power. And let's cover a bit of theory, a bit of math, because it is really involved in this process. It's tightly connected to machine learning. So everything starts with confusion matrix, with the errors or positive predictions we can get. So there are 2 types of right predictions, correct predictions. It's true positive and true negative. It means that everything that we meant to be negative is predicted as negative, and everything that we meant to be positive is predicted to be positive. And as well, there are two types of mistakes. First type is false positive, is when we intended it to be negative, but our model decided that it is a positive example. And false negative is when we wanted it to be positive, but got negative result from our model. Here are formulas, but I know that formulas are a bit boring. That's why let's take a look at this example. We have this. We have here slightly unbalanced data, and even though it has a really small difference, just 2 examples, we can see that it has affected our balanced accuracy results. So our accuracy is just the count of correct predicted values divided by the whole number of values. And balanced accuracy is average between truly predicted positives and truly predicted negatives, divided by positives and negatives. So we have truly predicted positives divided by whole number of positives. And we can see now, even though difference is not that big, in more unbalanced data sets, it can be really crucial. So beware to use balanced accuracy or other more precise metrics. And then we have recall. Recall is basically just a true positive divided by true positives and false negatives. By that we mean all positive actual samples. Balanced accuracy is used in tasks such as anomaly detection and class classification, and recall is used in one class classification task. So here we can see benchmarking for anomaly detection. There are pictures of something that you should keep your eye on. First, anomaly detection requires not one but two data sets. Be aware of that and prepare your data. Then we need to run our benchmark. And if we have some troubles with benchmark, we can see this orange exclamation mark. And if everything goes well, we can see this good green sign. Our scores are displayed here. They are in the middle of the screen. Usually you can see your usage of memory, you can see your accuracy scores, and overall score based on NanoEdge's internal metric, which is a combination of both balanced accuracy and memory metrics. To keep track, to see your progression in time, you can observe this plot. It shows you how balanced accuracy has been rising and how RAM and flash are being optimized. So it's quite handy to look at this. Even though the benchmark can take a really long time, so you're free to stop it whenever you want. If you have your perfect score, for example, you're aiming for 95% of balanced accuracy, and if you already have it and you don't have some more time to experiment, to wait until the benchmark is ready, you can easily stop it and continue with the perfect match this tool found for you. Benchmarking for one class classification is slightly different. It has only one section for data, where you can upload your regular signals. And then when you starting your benchmark, you can see this graph. It's showing the progress. And it is showing the abnormal signals it has found after testing some libraries. And of course, as well, it has its own menu with scores and RAM and flash consumption. Be aware of these constraints and pay close attention to the recall score. And of course, you can use tips. They will definitely help you to finish your benchmark successfully. Don't forget about them. So validation, it is probably the most interesting step, because here we can finally touch some libraries and have some experiments. It's particularly interesting if you have several locations, several situations. For example, we have two machines. We ran our benchmark on overall combined data, on mixed data, and then we want to find library that would work best for machine number 1, for example. Then we can, to do that, we need to upload some samples of data to libraries and see the results. For example, if we want to choose a library that would perfectly work for solely floor number 12, then we would definitely choose library number 2 because it has highest recall, right? But when we are talking about predicting on 2 floors simultaneously, we would definitely choose library number 1. And of course, you need to mind your execution time because people don't want to wait for too long. So please consider it. If you want to discuss with your colleagues some details or want to see some more information about the library they had found, more information about how it will work under different conditions, you can easily create your report and read more about the chosen library. And onboard results. First, I want to talk about some settings that are present when you're trying to compile your library. For anomaly detection is a special project. It has embedded knowledge in it. By embedded knowledge, we mean that this library has option store or not to store the states it had developed during benchmark. So we basically can download pre-trained or fully empty, not trained library. There is also this multi-library setting. We can enable it or disable it however we want. So if we want to run 2 or 3 models simultaneously, we should definitely check here that we want multi-library option, and if not, you can simply skip this step. And porting flow, it's probably not really hard for developers because all it takes is just download zip file with the library documents in it, and it takes some pre-developed functions for sensor reading and filtering your data, for forming your buffer to send as an input into your model. And when we got our functions, we can build project and integrate into it our model. Usually when we receive a zip file from NanoEdge, we can see their library itself, .a file, and then functions that will help us to run the model. And in case of anomaly detection, we can see knowledge library as well. And after deploying it, we can have our device feedback during inference time. So for our case, we got balanced accuracy on N class classification. We got balanced accuracy quite high, right? But it could be better. Unfortunately, we didn't have much time, but overall you can see that the model caught all the cleaning, but we have some false positives, which we should definitely deal with. And one class classification got a slightly worse results, but we can see that there is some area for improvement. For example, we can work with data a bit. We can collect some more data or delete some redundant parts of data and provide more relevant samples. So unfortunately, with anomaly detection, we didn't manage to make a good result on time because it required a lot of data from us. But in future, I hope we will get some more meaningful results. They're not that worse than this one, but we have decided to present these. So the main difference between N-class classification and one-class classification is that N-class classification simply has just more classes. You simply upload more files in your benchmark phase. That's all. No difference at all. And I want to touch a bit project specialities. By that, I mean types of projects. There are two types, dynamic and static projects. By dynamic projects, we mean projects that can learn during inference. So for example, we have trained our anomaly detection project and we have deployed it. We can simply choose option continual learning and make the model adapt to behavior of the environment. So it is quite handy when you have tons of devices in different places and you have no time to collect all the data. You can simply make this library work for you and do the job for you. And there are static models like one-class classification and class classification. They are static because every time you have some changes in your system, every time you have some changes in your data, you have to retrain it and reinstall your software to the target. So mind that, please. But they have a huge plus. For example, for one-class classification, all you have to have is just a set of good samples. It's quite good, right? Because you don't have to bother with collecting your data for a really long time. And for N-class classification, it is handy because you can, at any time, you can easily add or delete one class, retrain, and again, develop your software, which is good. Alexander, could you be so kind to continue?
Yeah, thank you, Darina. It was really insightful. Thank you for explaining us what to do when we want to work with the models. Basically, what I want to wrap up with on this presentation is some practical advices when using Nano Edge AI, because I appeared to be a DevOps in this project. So I was compiling and adjusting a lot of IT tools. So I actually saw some really good and nasty things during this process. So first of all, I want to remind to everyone that results in machine learning are vastly dependent on data you have. So you have the faulty data. If your filtering is wrong, if your sensors are on and off and all that stuff, you won't be able to get the data you want. You won't be able to get a model that would predict nicely, that would actually allow you to solve your problem. So that's super important. Second thing is a little bit more into practical things, like when you work with the model, it all sounds like, well, it's a very simple tool. You press it, then it compiles something, then it's done. Actually, it takes quite a bit of time, to be frank. Some of the models we have been training, they were spending like 30 hours of actually crunching the data. So you need some heavy CPU power, and then you might consider using some AMD Threadrippers or processors or something like Intel Xeon and stuff. So that's what we need. Then one of the recommendations that ST pulls in is that you need to have at least 2 giga of RAM per each core, and basically my recommendation would be to get as much RAM as you can actually. Virtualization is possible. So if you appear to rent some virtual machine to be effective, that's definitely an option. So you can obviously do that. And basically there are some limitations in the tools, like limitation of cores, and then some different behaviors with Linux setups and stuff. So you have to really remember some different practicalities, like always watch up your Linux swap memory use, so you can see that where the tool is definitely using more resources than it shall. So you can expand your RAM to and then it will help you to understand why it takes a long time. And well, using tips in the app, obviously, like Darina mentioned, that's really important. And then basically, my advice would be also to lean a little bit more into the Linux world, because it's simply in our situation, Linux outperformed Windows machines by roughly 30%. So that's some practical takeaways you can use to to spend your time more effectively. So that's basically all about the Nano Edge AI and our cooperation with ST. As you heard, we have been, definitely breaking some sticks during this process, and that was really fun. If you want to get a little bit more in touch with us in regards of developing your products and helping you to leverage either your just common skills in creating embedded products and electronics, or you want to know about how to test your products towards the compliance and different pre-compliance, as well as you considering manufacturing your products, that's all what we can help with our free business areas, where we provide a very strong shoulder to our clients. And apparently we'll be happy to address any of your ML products, where we can also engage some ST professionals to obviously help us if we come across some challenges with either tool chain or their processors and whatever else. So now it's a little bit, we had a little bit time off, actually. I'm really sorry about that, but I'm ready to have a few questions, and I will be checking chat, and I will be also ready to just you can open your mic and then just ask what is interesting for you. And in the meanwhile, I'll be looking into the questions. Well, I have only one question from Mike. How long does it take to benchmark a project? Well, I partially responded to it. First of all, it's really depends on the amount of data you fit your model with. With our 37K of records, I think the M-class classification was really taking a lot of time, and it took me, with like 26 cores assigned, it took me like 30 hours to actually crunch the data. So, but that's definitely not the super fast process. It was virtualized course, so maybe the real machine will a little do it kind of faster, but I didn't experiment with that. So basically you have to really set aside some time for crunching the data. So that was the question, the only question I had in chat. So if anyone is having questions, just open your mic and
I want to add a little bit about time of benchmark. It also depends on data. By that, I mean how distinguished your classes are. For example, if you have really similar abnormal and normal samples, it can be quite hard for library to break it, to find the solution.
Definitely. I have a question from Sergey. I have a right hand. Sergey, go ahead.
Hello. Yeah, basically my question is if you have any idea about the model size difference in Flash and RAM, depending if it's a dynamic project or static project. How big the difference is in the system demand. Which one would you recommend to use on the small embedded target? Thank you.
Darina, can you take this one up? Or you would want me to answer?
No.
Hello.
I will add something. Yeah, you can definitely.
I can help also Lucas Valverde. I work in Nano Edge AI team as a technical leader. So about your question, indeed, depending if you're on static or dynamic model, so anomaly detection, as we see, you will have maybe more needs on RAM for the anomaly detection instead of all the static model where you will need more flash, because indeed we are taking a huge buffer that is constant, so it's static, and we can put it in the flash instead of dynamic. So anomaly detection, we are learning the behavior on the microcontroller. So we are using RAM to adapt the variables and so on. So yeah. And
Okay,
about the size, it will depend on your data sets first, and then of the complexity of the library you will get.
So, but if we're comparing, if you take the same data sets for the dynamic project and static project, then for static project we'll have more flash use and less RAM, and the dynamic project is less flash and more RAM. Okay,
exactly.
Thank you.
Yeah.
Thank you.
Sorry, thank you, Lucas, for follow up here. That was the good one. We have also the question in chat from Mike about using NVIDIA, I believe, for crunching data. We actually didn't use any acceleration like that, so I can't really say much. I have a hand from Claude Laurent. Please go ahead.
Yes, the question is in relation to the application. I have also a question related to deployment, but it's more, I think, in the sense of development. But so what you see, you show experiments about pumping the washing machine, but what about signals which are more in high frequency, like RF, or if you have currents, like for example, in windmills where you have high frequency currents from the converters, which are in the kilohertz. What about what the question is about, what the bandwidth of the signal, can you deal with this kind of high capacity bandwidth, or is it limited? Do you have a limitation to low frequency domain, like pumps?
Yeah, good question. In fact, NanoEdge AI consider really that everything is mathematics. So we are not very worried about the fact that we are in a high frequency signal. But as Darina showed very well, we are taking a window. So depending on the window you want, if you are going to a data rate very high, you will get in troubles with your memories. So that's the limitation, in fact. But if you are on a huge device, well, huge, for a microcontroller on a device with maybe hundreds of RAM, you can try to play with these kinds of signals with really high data rate. We have some demonstration with current, and we also have some demonstration where we try to find the default of bearing systems. And in fact, bearing systems have anomalies higher than 10K. So yeah, we are playing with this kind of use cases.
Mm-hmm. Interesting. And another question is so this kind of concept is what we call edge sensing. So meaning a sensor become a node. Is there a concept where you interconnect these nodes together, or and then you have a modelization of the interconnection kind of distribution, or is it the computing is per sensor? Do you see what I mean? Is it meaningful? Or?
Well, yeah. So we have two options, in fact. The classical one is what we see today. We are doing all the computation on the MCU, and doing this, in fact, we just take the data from sensors. It can be one, and as Darina showed, it can be multiples. So that's the first answer. The second is that we are also trying to do some solutions for sensor, but really to do the machine learning inside the sensor. So at ST, we have a project that is called Intelligent Sensor Processing Unit. So in this case, everything is in the sensor, but it is just this one, regarding your question, we don't have nodes or we don't have communication between sensors, but with the ISPU sensor, you can just put your MCU in sleep. Okay, so you are very in low battery mode, and you just let your accelerometer trying to understand when you have an abnormal behavior in the vibration, for example, of your system.
Okay. Yeah. The question was more related to the meshing, because right now, everything is concentrated at one place. For example, on a windmill, we have thousands of sensors. And then each of sensor is concentrated to a node. Each node concentrate to the control system, and then the control system work and raise alarms or stop. And so the question is more to, because the idea is now to deport, in fact, the intelligence on the sensor, if I understand correctly. And the question is the capacity to mesh, I mean, and then to, because at the end we have to reconcentrate to the control system.
Yeah,
Well,
I
if-
understand.
I understand. Yeah.
I have your point.
Yeah,
And it's not in the scope of NanoEdge AI,
No.
this kind of
yeah.
solution.
If
Even
if
because,
sorry, please go ahead, Louis.
yeah, even because if we take the signals of all the sensors from a pump or a huge pump, or in this case that you can imagine, we won't be able to run it on a microcontroller. And the scope of NanoEdge AI in ST is really to run for microcontroller Cortex-M based. So that's why we don't really go in this direction. And I would suggest to have maybe a look on the MPU we have in ST that contain much more memories and multiple processing. So yeah, maybe this kind of projects could answer, but it's not the case for NanoEdge.
Okay. It's applied also for redundancy. For example, sometimes we need to have sensors which are redundant in case one is breaking. So we have still one working. And but I'm very interested in the, in fact, deployment, the application part, practical things. Yeah, really interesting.
If I may just wrap up super fast, is that Claude, you can look on the data as at different abstraction layers. If you can make your small MCU to process some few sensors and then generate, like in our case, one bit of data saying yes or no, and then at a higher level, because anyway all systems are hierarchically built up, so you cannot just have one super big processor just doing it all, because then the processor would look like a Intel Xeon processor or something like that. So but in fact what you can do, you can, by multi-layering, you can pack your data into edge process data, and then that edge process data will be somewhat archived. So in that very small data stream archive can go to the higher level processor or the application processor that can in fact deal with redundancy, deal with with more sophisticated decision-making process, like if this is now an abnormal situation or not. That would be my recommendation, at least from architectural perspective. All right. Well, I believe we are a little bit far off with the schedule, so I have to close the Q&A session for now. I'm really sorry for that. So basically, this is the very last meeting for this year. From EKTOS, we'll be coming back to you Q1 with our schedule for next year, where we'll be putting more efforts into ML, definitely, and we'll be preparing for you really nice materials. For those who will provide a feedback, there will be a feedback form right after the end of this meeting. You will get a slides copy. And using this opportunity, I really want to wish you a Merry Christmas and Happy New Year. I know there are a couple of weeks more before we get into it, but I'm very much looking forward to get in touch with all of you and do some very nice projects together. So that's my last word, and I want to say thank you to all of you who delighted your evening for this interesting topic. So that's a final word from me.
And we as well have feedback form in comments.
Yeah.
So please fill in.
That would be nice to get some ideas what you would want to know more about the topic. So that's all from me.
I would like to thank also you and Darina really this demonstration. I had some ideas and some advices that I will give to the team, and we also will try to improve our product with this. So thanks a lot.
Thank you for joining us
Thank you
today.
too.
We really
job.
appreciate your company. Thank you. Thank you, ST.
Yes. Thank you,
Yeah.
guys. Merry
Thank you
Christmas.
very much to everyone.
you.
Have a good evening.
Thank you, everyone.
Bye bye.